Hello students, how are you? I hope you are all doing well. So today we will study the topic conversion of MCG into an ammeter and a voltmeter. MCG, the full form of MCG is moving coil galvanometer. Okay, and we all know that the moving coil galvanometer is a well-defined instrument to, or we can say, instrument to measure the current and its direction in an electric circuit. Okay, and how we can convert that moving coil galvanometer into an ammeter and into a voltmeter that we are going to study now. So basically, the box diagram of galvanometer can be drawn like that, where the galvanometer, like the symbol for galvanometer is G, that can be drawn like here, and then the resistance due rest, which is like the we know that every we can say every electronic gadget will have some resistance. Okay, so the galvanometer will also have some resistance, and that resistance is named as RG, capital RG. Okay, so that's how we represent. Uh, that's how we represent a moving coil galvanometer. And the deflection, or we can say deflection from the equilibrium of an galvanometer is given as deflection of the needle, deflection of the needle of galvanometer of needle of the galvanometer, or MCG I am writing. Moving coil galvanometer is, it is denoted by phi equals to NAB upon K into I. Okay, I'll tell you the meaning of this N, A, B, K, and I. So here N is the number of turns. Here, right here, N is number of turns with number of turns of the coil which is used in the galvanometer, and A is the cross-sectional area, and B is the magnetic field. Okay, and K is the torsional constant. Here the K is torsional constant, and I is correct. I is correct. Okay. So now the first process we are going to do is the moving coil galvanometer into an ammeter. Okay. So first one is conversion of an MCG into an ammeter. Okay. So before converting the MCG into an ammeter, what we should know about the properties of ammeter. Okay. So what are the properties of ammeter? We know that ammeter has infinite ammeter has zero resistance. Okay, if we talk about an ideal ammeter, then it will have always uh, zero resistance. Okay, so here we cannot obtain the ideal ammeter, but what we can do, we can go to the approximate value, or we can say somehow it will act like it will act like ammeter, like it will have some very small resistance. So for that, what we need to do is we have to convert the MCG such that it will have very small resistance, or we can say near to zero, so that it will act like ammeter. And if we, and after the conversion, when the MCG will be converted into an ammeter, it should be connected in the series connection with the electrical circuit, because we know that after all it will be going to measure the current, and we know that ammeter always ammeter is always connected in the series connection, that we should know. Now if we want to convert the MCC into an ammeter, so what we'll do, we will add here in the process, we have to add one shunt resistor RS. Okay, shunt resistor or shunt resistor is a very small resistor, we can say, or we can say very small value shunt resistor. We have to add one shunt resistor in parallel connection with galvanometer. Galvanometer. Okay, then only it will be converted into an ammeter. So let's draw the diagram again. So it will look like, so this was the original galvanometer. Okay, now we want to convert it into the convert into the ammeter. So we have to connect one small resistance, or we can say shunt resistance, in parallel connection with the galvanometer. So we should connect it with a small resistance RS in the parallel connection with galvanometer. So this whole setup will be called as ammeter. Okay. So this whole setup will be called as ammeter. And we can box it out also. So we will not be getting confused that how much portion will be called as ammeter. This the whole portion, or we can say the whole setup of the galvanometer, where the one shunt resistance is connected in the parallel connection with the galvanometer. This will be called as ammeter. So it will be named as ammeter. So if we talk about ammeter, then one thing we should click in our mind, that we are going to measure the current. Okay, if we are going to measure the current, then we should know the current sensitivity of the galvanometer also. Okay, at the end it is the galvanometer only which is converted into the ammeter. So we have to calculate the current sensitivity of the galvanometer of the, or we can say current sensitivity of the ammeter in this case. So what should be that? Basically current sensitivity is basically it is given by, or we can say expressed by, like deflection per unit current. Okay, that will be called as current sensitivity. So what is the current, how we can calculate that? We have one formula, that deflection is NAB upon K into I. So if the I will go in the denominator of deflection, it will become current sensitivity. So current sensitivity of the galvanometer, current sensitivity, current sensitivity. Okay, and it is given by deflection, deflection per unit current, deflection per unit current. Okay, so therefore it will be phi upon I, phi upon I, it will be and AB upon K. So this will be the current sensitivity of the galvanometer. And while the manufacturing this galvanometer as an ammeter, so the manufacturer will decide that the current sensitivity should be high, and how he can increase the current sensitivity by just increasing the number of turns. Okay, so we can make a point here that current sensitivity current sensitivity can be easily increased by the number of turns. And if we increase the number of turns, we will get the high sensitivity of the galvanometer. Now the second thing is conversion of galvanometer into a voltmeter. So the second thing is conversion of an MCG into a voltmeter. Okay, how can we convert an MCG into an voltmeter? As we know that the resistance of voltmeter is, or we can say an ideal voltmeter is infinity. Why it is infinity? Because we know that we can say voltmeter is always connected in the parallel connection. Voltmeter always connected in the parallel connection, so that uh, uh, we can say the voltage across any resistor, or we can say any electric appliance can be find out. So that's why we have to convert our galvanometer such that it will have a large, or we can say enormous resistance, so that it will act like a voltmeter. So for that, what we have to do, first of all, galvanometer like already have some resistance, that is Rg, and now our task is to like connect a higher resistance. Okay, connect a higher resistance with the in the series connection with the in the given galvanometer. So then only we will get the voltmeter. Okay, so if we connect, okay, let me see. So the galvanometer, add a add a in place of high we should write large resistance. Add a large resistance in series connection with galvanometer. So we have to connect with large resistance in series connection with the galvanometer, then only we will get the voltmeter. So let's connect that. This is the galvanometer up to this part. Now we have to connect one large resistance. Okay. One second. Wait. One large resistance we have to connect here. Okay. So here this resistance is Rg, and this one will be a very large resistance R, and basically it is denoted by Z. So this whole setup will be called as voltmeter. Okay. So this also we can mention in the dotted form that it will act like voltmeter. Voltmeter. Okay. And now if we talk about voltmeter, then we should also know that what is its voltage sensitivity. Okay. So voltage sensitivity is nothing but deflection per unit voltage. So that will be called as voltage sensitivity. And how to determine that? Again, we have one formula for the deflection, and from that only we can find out the voltage sensitivity. So we know that, as we know that, because deflection is nothing but phi equals to NAB upon K into I. Fine, we have that. Now, what we have to do, we have to divide both of this side by voltage V. So we will get NAB divided by K into I upon V. Fine. Now, phi upon V will be given as NAB divided by K, and as per the Ohm's law, V can be replaced by IR. So it will be I upon IR. So the equation will become as phi by V equals to phi by V. It will become as phi by V equals to NAB upon K, and I will be cancelled out, and we will get 1 upon R. So this will be the voltage sensitivity of the galvanometer. Okay, this will be named as voltage sensitivity of the galvanometer. And it is not like if we increase the current sensitivity of the galvanometer, it will automatically increase the voltage sensitivity also. Okay, if we increase the number of turns, then obviously if we are increasing the number of turns, then as in the proportional way, its resistance also will be going to increase. Okay, let's say, for example, if if the number of turns is doubled, then obviously the current sensitivity will be doubled. But what will happen in case of voltage sensitivity? If we double the number of turns, then the resistance will also be get doubled. And those in this formula, in the voltage sensitivity, it will be turned as 2n and it will be turned as 2r. So 2 and 2 will be cancelled out, and the voltage sensitivity will be same. So we cannot expect that when we increase the current sensitivity, it will increase the uh, voltage sensitivity also. Okay. So now in this topic, one thing is left, that what will be the net resistance in case of uh, like moving coil galvanometer into an ammeter and moving coil galvanometer into a voltmeter. So in the first case, what will be the we can say resultant the result we can say the resultant resistance, it will be, in the first case, let me derive, 1 second. The equivalent resistance when mcg is converted into an ammeter. Okay. If an mcg is converted into an ammeter, then we can see that here one shunt resistance rs was connected in the parallel connection with the galvanometer, where the resistance of galvanometer is Rg. So we will apply the same rule here, or the parallel connection rule. So in parallel connection, what is the equivalent resistance? It will be 1 upon R equivalent will be equals to 1 upon Rg plus 1 upon Rs. Now 1 upon R equivalent. So here the LCM will be Rg into Rs, and in the above it will be Rs plus Rg. This will be the equation. And later on, the equivalent resistance will be, it will be Rg into Rs upon Rg plus Rs. This will be the equivalent resistance of the galvanometer when it is converted into an ammeter. Now, if we roughly talk about, like, when we know that the Rg, the resistance of the galvanometer is very high with respect to the shunt resistance that we have connected in the parallel connection, then the special case we can see when Rg is much greater than Rs, then Rg plus Rs, it will be approximately nothing but Rg only. Let's say, for example, if we see the value of Rg is, for example, 1000 ohm, and the value of shunt resistance is, let's say, 1 ohm or 2 ohm, then if you add 1 in 1000 or 2 in 1000, it will be approximately 1001 and 1002. So it will, we can say that the nearby value is 1000 only. So that's why it is Rg. Now, if it is Rg, then we can say that it will be given as, like, the above equation will be formed as Rg will be, sorry, R equivalent will be here, R equivalent will be, it will be Rg into Rs upon Rg only. Then Rg and Rg will be cancelled out, and the galvanometer will be, resistance will be cancelled out, and the R equivalent will be Rs only. And why it is important to write R equivalent equals to Rs? Because we know that we have converted our galvanometer into an ammeter, and the resistance of ammeter should be as small as possible. So the resistance that we have connected in the parallel connection was already a shunt resistor, or shunt resistor is always have some negligible value, like the 1 ohm, 2 ohm value, or sometimes less than that also. So that's why it is important. Now, in case of voltmeter, what will be the case? Second case, second case is when an MCG is converted into a voltmeter. We know that in case of voltmeter, we have connected one large resistance in the series connection with the resistance of galvanometer. So here the equivalent resistance will be, it will be R equivalent will be nothing but Rg plus R. So this will be the net resistance here. Now this time also we'll take the case when, if R is much greater than Rg, then this time also what we will get? We will get that Rg, R equivalent, it is approximately equals to Rg plus R equals to R only. Or we can say equal to the value of the higher resistance, or that's what we wanted in case of voltmeter, because voltmeter always have a we can say very high value, or we can say near to the infinity value, or we can say mega ohm or giga ohm or something. So that's why very high resistance we have to connect in the series connection. So that's how any like one galvanometer can be converted into an ammeter and voltmeter. Okay. So now if you have any doubt, then you can ask in the comment section and I'll be happy to answer them in the next video or in the comment section itself. Thank you.